So I was asked in the elevator a few questions about the exam and the part of the course that is given by the teacher assistant, the exercises, whatever you call it. And look, the main focus of the course is the lectures. And I don't know how it is in China nowadays, but in Israel, in high school, they are actually teaching you how not to learn. What do I mean? They come with a set of, on each subject that you study, they come with a set of 50, 100 exercises that one of them will appear in the exam. And what do? Most of the pupils just sit down, solve all the 50, and the main challenge is to identify which one of those 50 is a question that appears in the exam. That's not what I want to do. Look, for two reasons. One of them, it doesn't prove that you have learned anything. It proves that you went through all those 50 exercises. And second of all, look, the world is moving forward. Nowadays, if you want to find a solution to a problem that was solved, you can do it very easily. So ChatGPT 3.5 hallucinates, 5.4 is a bit better, but within 5-10 years, anything that was ever solved, you would be able to find within a few minutes. And well, that's not the purpose. The purpose is that you will understand the material, understand the basic assumptions, the whole philosophy of how to handle a problem and how to come up with a solution. So I'm trying each time to invent an exam that is not similar, not to your home exercise and not to previous exercise. Sometimes I do it better, sometimes I fail, but that is the purpose. And I can even be more, give a stronger statement. In an exam that has 3 or 4 questions and takes you more than 2 pages, you're doing something wrong. Because I'm not going to check whether you have studied all the properties of the Hermite polynomials and know to do those integrals. Well, probably some of you do, some of you don't, but any time that I give a problem that seems to have a solution by doing cumbersome math, the answer is you're doing it wrong. So what I always suggest, and students have an extremely hard time with it, is not to start studying by going over on all the previous exams and going over all home exercise that you had, and then they get very angry. It's a question that we ran into in the exam, a question that wasn't in the, we didn't do something similar to it at home or something like that. Read once or twice the whole material from the beginning and stop at each stage and ask yourself, what actually did I learn here? And that will be much more useful to go through the exam. Of course, you need some basic mathematical proficiency. If someone comes and says, I don't know how to diagonalize a 2x2 matrix, I'm sorry, that's something you should do. Or how to perform an integral on a sinus. Well, that's the level. I don't expect you to run into very cumbersome mathematics. If I give a 3 by 3 matrix, usually there's some trick to do it very fast. Okay, questions about it?
Did you suggest to read any book or just to go?
Look, as I said in the beginning, all quantum mechanics books are quite good and cover the material. There are the older books that I think have everything in them, like Choose Merzbacher, Park, Schrieffer. All these books are good. The point is that quantum mechanics, as I said in the beginning, is something like a mathematical theorem. So all books, more or less, are very similar to each other. It's not like in solid states that some of them cover these phenomena and others cover other phenomena, and some of them approach it from the experimental point of view and some from the theoretical. Quantum mechanics has one main route to it. And then you have excellent but very long books that overdo what the Messiah, for example. Messiah is the Cohen Tanuji of the generation before Cohen Tanuji. So they cover everything with a lot of pedantic. It's very good to go over them. I'm not so sure that you need it, or it's a wise investment of time. Cohen Tanuji is excellent if you want to go into a concrete problem that is important for your research, and you want to see what was done and how should I think about it. But reading a book or going over the notes, I think is very similar in this case. It's not very different. Additional questions?
We have the sum of the lectures in the module. I see the sum of the exercise, the lectures.
Well, you have the whole lecture given. Every book covers it. And you're allowed to bring to the exam any materials that is not connected to the internet. Not because I mind that you will go over the internet. Actually, nowadays I a bit do mind, because that kills the ability to find any questions there. No, but mainly so you won't contact someone who will solve your exam. Once you have your Neuralink connection in your brain, and in 5 years, I don't know what you will do. So the point is not to memorize. There's nothing to memorize. On the other hand, again, it has a downside. I've seen it too many times. People come with such a bunch of books and notes and spend the whole time of the exam leafing through it, trying to find to what it's connected. You should know what's going on there. No one expects you to remember factor 2's or minuses or things like that. That's not the purpose. Anything else? Okay, so what we'll do in this lecture is basically continue from where we were and finish up. I hope we'll finish up. If not, in the next lecture, angular momentum. So just as a quick reminder, we started by just writing down the operator, and the basic idea was that if we know the operator for R and we know the operator for P, which we know how to write down the operator for L. Okay, and then of course we can look on L squared, the amplitude. And we can look on each one of the components by itself. Okay. And we wrote down in Cartesian coordinates, we wrote it down in spherical coordinates. And the main thing to remember from this whole game is basically LZ and L squared commute, meaning they have the same eigenvectors as a basis. And instead of LZ, I could write here LX or LY. It doesn't make any difference because this is just me choosing where my axes go, and me choosing how the axes go should not determine the physics of what's happening here. But, and a very important point is that they don't commute among themselves. Actually, a question of understanding. Why is there here a H bar?
Because of the units.
Exactly. Here I have something that's L squared. The units of angular momentum are H bar. But here I have just one power of it. So just so this equation makes sense from the point of view of units, I have to have there a H bar in it. And as you know from the end of the previous lecture, we always had there n times, let's say, n plus 1, and L times L plus 1, and when we had only m, we had always a H bar before it, for the same reasons. Units have to be conserved. So basically, we decided that we'll look on the eigenfunctions of Lz and the eigenfunctions of L squared, and we decided that it's H bar just for units and m, which we are close to proving that it's integer, but not yet there. And we are also able to write down L and M as some something that depends on theta and something that depends on phi. And we even showed that and just from the point of view that we should have, after going through 2 pi, the same wave function. And let's say if I ask a question of understanding, why for K, for example, we could have a continuous spectrum of the eigenvalues of P, while for L and M they are discrete. Why is that?
Because they are eigenfunctions of.
No, that's mathematics, physics.
Because
Because the angular momentum is only conserved under rotation, and we cannot move.
You're on your way, but even simpler. Because any space that is limited in its values, and theta and phi are limited between 0 and 2 pi, and between pi and minus pi, between pi and 0, once they are limited, they're quantized. We saw it also for P in the periodic boundary conditions, which are very similar to what happens here with theta and phi. You go through a number, you go through the space, and you return to the same point. Same thing, and there P was quantized, actually very similar to this. So the physics is very simple. If your space is infinite, you have a continuum. If your space is finite, you have quantization. That was the same logic that we got for the problem of a particle in a one-dimensional well. As long as it couldn't run away to the infinity, it was quantized. Once it can, even from one point, in one direction, then you have a continuum. Very basic and very simple. So clearly you had to expect here that angular momentum will be quantized. The exact form already depends on detail. Yeah.
And anytime we have an eigenvector with two variables, and we have two operators that are diagonal on that eigenvectors, if we have the number of operators, we have something that creates all the space.
Mm-hmm.
Because we have here two operators, and we have the two eigenvalues, and we have determined everything, right?
Right. Basically, because of this symmetry here in theta and phi, the independent symmetry. So, but you'll see that theta does depend on n. That we'll see today. Okay, so how do we move from here? Very similar to the same ways that we moved for harmonic oscillators, the same logic. We define two operators. In this case, we call them L plus and L minus. You can see immediately it's the same constructs that we did with x and p. There we had a few constants before it, but it's exactly the same logic. We take two operators that don't commute, x and p don't commute, Lx and Ly don't commute, and we write them down and see what happens when we apply them on the eigenvectors, and that's what we're going to do now. So towards the end of the previous lecture, we saw that M is limited. And we did it. We can go back and see how we proved it. Now we go on and ask the question, which is very similar to the questions that we asked in an harmonic oscillator. Applying A or A bigger on the eigen function of the number operator, what happens? So here we are asking what happens when we apply L minus on Ln. You can guess what happens. It will change the value of, well, that perhaps you couldn't guess, of n by minus h bar. And we'll show it in a moment. L plus will raise you. So let's see what happens. So why do I write it in this way and not just this guy? Because this guy will enable us to see what happened to Lz. I claim that it will move n. Let's see that it doesn't. So okay, someone has a clue from where did I pull this one out?
From the commutation relation between Lx and Ny.
Right, I just write down the commutation Lz and L minus, that changes direction and gives me an additional value of L minus. Okay. Lz on Lm, I know what it does. Okay. These are scalars, numbers, so I can pull them out. Good. So we started with this function and ended up by applying Lz on this function. We got this result, meaning same game exactly as we did for creation and annihilation operators. For the harmonic oscillator, we move down 1. I'm writing here C because it's not yet normalized. Same stories that we had for harmonic oscillator, nothing changed. Okay, so now I have to normalize it. How do I prove it? We did it in the previous lecture. You remember that we took L minus and applied it to Lm and multiplied it with one another in order to show that it has to be positive. Same calculation. So it's the same prefactors that we got there. Same calculation exactly. Okay, so until here, we play the same game, similar game to harmonic oscillator and got these results. Pay attention, all these L minus and L plus move you in the Z direction. It doesn't do anything to the L square value. Okay, what conclusions can I draw from here?
It's a plus.
This is a plus.
0.
Will be 0 just because of this. So these fulfill the demands that we had before, that M will never go above L. Just another way to express it. And it has the additional contribution that we can use it to calculate actually LL. Same way that we used with n equals 0 to calculate the harmonic oscillator. It's just a repetition of the same bag of tricks that we used there on a different space. Also 0. Just put it here and see that it goes to 0. So we have here an upper and lower limit, not surprising. In between, M jumps just by plus minus 1. That's the only games that they can do here. So these are the only values that I can get for M. So if someone gives me a value of L, So actually, in this very innocent and simple calculations that we performed here, we actually got two extremely strong physical consequences. This explains all of chemistry. The different columns in the periodic table come out of this. So it's a consequence of angular momentum. Now, why is that relevant? And you will do it in detail the next semester in Quantum 2. Usually this would come immediately after it, but unfortunately we're unable in this semester to do it. Just basically because the Hamiltonian of any spherical symmetric potential is commutative with L square. So the eigenvalues of theta and phi will be the eigenvalues that we wrote there. And since there's no spatial preference for a potential of an atom to be in one direction or another, it has to be a spherical symmetric Hamiltonian. Our eigenvalues, no matter how they look in R, will have to have this degeneracy. That's that. So all of chemistry is hidden here. I have another strong statement. L must be integer or half integer. Now, integer you can more or less see here. Because if it's not integer, you have nothing to stop my ladder for continuing going up and down in both directions. And then you could have minus infinity result, meaning you have no minimum. Very bad. Second, y half, you can write it down and you'll see that in this case it will stop you, let's say L equal a half. You'll have another value, m could take the values half and minus half and stopped by what is appearing here. It doesn't work for any other fraction. Now you can stop me and say, but do we see half integer values in nature? The answer is yes and no. What do I mean by no? For angular momentum, no. But we have another physical quantity, which is the spin, that doesn't exist in the Schrödinger equation, but it has to obey the symmetry of space. But there it actually gives us either half integer or integer. So spin can be half integer. Therefore, you sometimes refer to spin as angular momentum. Why? It's not angular momentum. It's not r cross p. has a totally different origin. Nevertheless, the symmetries that it obeys are exactly the same symmetries.
It follows the same algebra, right? The commutation
Exactly.
relation.
That's what I mean by saying it follows the same physics. At the end of the day, now I can give this bold statement. At the end of the day, the physical properties of any system are defined by the commutation relations of the operators that describe it. So although spin is definitely something that is not R cross P, it follows the same commutation relation, and therefore it has the same symmetries and properties that we have seen here. Okay, so this is the whole physics that we pulled out actually without sweating, without going into too complicated algebra. You needed to know how to count here. That's more or less all you need here. Nevertheless, we still feel a bit bad that we didn't write this function theta. What is the eigenfunction in theta and phi coordinate, in theta coordinate of the eigenvalues of L squared? So now we'll spend some time in doing this a bit more complicated mathematics in order to pull them out. What will be our basic first step? These relations the same ways that we pulled out the Hermite polynomials for the case of the harmonicos.
In this case, are Legendre polynomials, right?
Yes, but not of theta.
Cosine theta.
Of cosine theta. We'll see it. It's no magic here, just straightforward algebra. So I have to stop here being lazy and write down the operators in the spherical coordinates. No magic. We wrote down Lx and Ly in the spherical coordinates last lecture. Just write it down and get to this point. So it's one of the few cases that you see cotangents, which is 1 over cosine in this game. Okay. And we will retrieve LL from this condition. Okay. What happened to the phase?
It's equal to 0, so we can multiply both sides with the phase.
Now, what happened to phi? Well, here I can simplify it. What will this derivative of phi do? We recall that phi is some constant I and phi. We'll pull out n, but m is equal to L, so I can replace this whole thing by You're worried. Okay, I'll write down it in 2 steps.
Because we are missing the phi as the function.
Okay, so to remind us, right? This is LL and this is L. This is theta and this is C. Okay, and this guy we actually know. Okay. Now I use this guy. This, you agree, we don't need. It's just a constant. Okay, so we have plus okay. This doesn't have any influence on this. Okay. This guy has no influence on this guy, right? This I can perform. This will give me simply ILM, sorry, IL times e to the power IL phi. This guy I can just eliminate. IL times I have here, should have here I times I, so it's not, sorry, it's minus. So good that we did it. We have now the correct sign. Okay, so nothing especially clever, we're just writing down the solution and seeing what we get. So, at the end of the day, we have here a first order differential equation. That's good because usually first order differential equations we can solve. It doesn't have anything extremely pathologic, we can do it. So what do we do here? Divide by theta. Forgot what is a cotangent. What do we do anytime we see this guy?
Integrate.
Before we go to integrate, let's do it easier. What type of derivative gives me 1 over the function times the derivative of the function?
The ln.
Ln. Why do I do it? Because it makes integration easier. Should shoot me. Cotangents is the other way around.
Okay.
Perform integration on both sides. Okay. Integration of a derivative of the function is the function. Okay, if I perform a derivative of cosine, what do I get?
Sine. Minus sine.
Minus sine. So how do I get some result like this? Oh.
Divided by cosine.
Because derivative of ln of sine will give me 1 over sine below. Derivative of sine will give me cosine. Okay. I have a constant from both the two, so I can push them here.
You just do the cosine, you put it into a differential, right?
Just one over whatever is within the ln. Derivative of what's here, cosine. If I don't remember this trick, I just open the table of integration and put in cotangents, and you'll see that that's the result. Okay. Well, I don't like lns. I don't like C. Ln of some other constant. A constant. I can find it as I wish. I don't like this guy here. Makes life complicated. So I put it inside here. So what will be A? According to the normalization. So what do I need from normalization? From where is the additional sign? The Jacobian we are doing here spherical coordinates, we have to take into account the Jacobian. And can open any table of integration or try to find a trick to do it. Not extremely complicated. And basically, since you have here square, you can replace it with cosine, and one is the derivative of the other, so life is good. And you get that A, L, L And of course, all of this must be equal 1. So that's normalization. So everything till this minus just straight out of the integral. And I put in this minus so it will fit the definition of the Legendre polynomial. From what's written here, it could or it could not depend on some power of minus 1. It doesn't matter if it's minus or plus. When you're squaring it, it doesn't make any difference. So, So what do I do to find the value for any n?
We just need to put the operators, right?
I use the operator whatever number of times do I need to go down from L to n, and that's that. So after treating the constants, so this I can get out of normalization. The things that are important for physics is basically applying it L minus n times, because you want to go down from L to n. And noting that if you use L minus just to keep units correctly, you have to divide it by h bar. So if you want to scare people, you write down YLM not yet finished. So it's cumbersome, but it's very clear what we do. We take our solution of LL, we obtained relatively cheaply, and perform L minus N derivative L minus M times. So that's it. Now, the good old days, you would just go back and look in the textbooks. They would have a table of at least some values of Lm. Nowadays, you can just Google it and get values up to 5, 6, whatever you get, and you have the whole solution of the thing. Okay, nevertheless, I'll write the few first values just so we'll have some feeling what they give us. The simplest case, L equals 0, M equals 0. There's no additional values of M here. That's that. So the wave function of the L square, of the angular momentum square, or of Lz, or Lx, or Ly, in this case, is just a homogeneous, and 1 over square root of 4 pi you could have guessed. Those two results you could have guessed immediately. It has to be homogeneous because there is no, it's symmetric. And second of all, it must be 1 over square root of 4 pi because the normal integration of sine theta d theta d phi gives you 4 pi. So what else can it be?
And also, if we take the sphere, it's the phase factor is 4 pi, and we need to normalize.
Power of 2, so it's 1 over. Can't be anything else. So that's easy, simple, and completely counterintuitive, because this is the spatial distribution of the wave function of, let's say, an electron around an atom. And you remember that in all the good old drawings from high school, you have an orbit. No, it's homogeneous around the atom. If you really want to plot what is the probability of finding an electron in the ground state of any atom for the first state, it's homogeneous. There's no any kind of orbit around it. Nothing. If you stop for a minute, it's even worse. Because in the classical intuition, where we're looking at the electron orbiting the nucleus, why doesn't it fall in? Because the nucleus is positive, the electron is negative, should fall in. So the answer is the same answer why we are not falling in the classical term. Why aren't we falling into the sun?
Because conservation of angular momentum.
Exactly, we are in an orbit around the sun. So the answer for the atom would be we're in an orbit around.
But the problem with that will be that it's an electron accelerating, and it should emit something and lose energy, and therefore.
So the answer is it has no angular momentum. L is equal 0. You calculate its the amplitude of L squared, 0. What is angular momentum in any direction? 0. And nevertheless, it doesn't fall into the atom, just because the wave function has some distribution in space. Okay, so you tell me, okay, that's not so bad. Let's look on the first case where we have angular momentum. Okay, that will be y1, 0 or y1 plus minus 1. I have three solutions for the case that L is equal 1. Okay, let's go into it and find out what are the solutions. Okay, these are the solutions. Okay, if I'm looking on this guy, how does it look? Let's take actually the 1, 0. Doesn't depend on phi, right? So that's the first thing that we see. So in the xy plane, it has no dependence. Where is cosine maximum?
0.
At 0 or pi? Actually, so if I'll draw the distribution of this function, and I'm choosing, because it doesn't depend on phi, a particular value of phi, just to keep it on the two-dimensional case. So this is the xy plane. I just choose some direction. This is z plane. It has a maximum at theta equals 0 or pi, and a minimum at theta equals pi over 2. So here it's the minimum, here it's the maximum. So the probability is large that it will be in the two directions opposite to z, and minimum on the xy plane. 0 actually there. And these guys are the opposite. It has a maximum on the theta equal pi over 2, that's the maximum of the sine. It has a phase, but if I'm squaring it, it doesn't depend on phi. And the minimum that it will be in the opposite direction, in the two plus minus z direction. You can also, there's nice 3D plots of it. You can find it by Googling it. You'll see a lot of nice pictures of this. The main point I want to pull out of here, again, has nothing to do with the picture of orbits. The only thing, perhaps this has some intuition about an orbit in XY. This has nothing. Well, not surprising, it's m equals 0. It has no particular operation. This has plus minus m. Why is that? Let's go back to the physics of momentum. Momentum had a solution e to the power I kx. Where did we get the direction? Derivative of this guy. Here's the derivative of the phi. Will give me the direction as plus m or minus m, depending on the plus minus here. So we have wave functions, we can plot them. They have little, perhaps for this case, it has something to do with our intuition of orbits. All the others, no. Okay, so we'll have here a break for 15 minutes, and then we will show the connection between these y's and the Legendre polynomials. Okay, how did I get this differential equation? Basically, we have written explicitly L squared in the spherical coordinates, and we had here a second derivative in phi, but we know how the function in phi looks, so it just gets us m squared, and we can get rid of phi, and we're left only with equation, a differential equation on theta. Okay, let's change coordinates. So instead of looking on a function of theta, we'll look on a function of theta cosine theta, which we term as x. And we have to write down the derivatives, which are period to do theta. So far, just the chain rule. This guy we know to perform. And this is just to the x. Sine square plus cosine square is 1. So, all that is needed here, to go back here, and anytime we have theta, replace it by x. Just sine square is 1 minus cosine square. Any times that we have dot to the theta, we put in this guy. And here we have the connection of sinus theta, and here we have a multiplication by sinus theta, so it's all the same. Why is it interesting? Basically, it's interesting because this is an equation that we have a solution, at least for the case of note that actually, interestingly, here the solution for L and 0 is the easiest, while we solved it for L and L from the other way around. So for m equals 0, we lose all of this, and we identify that what we have written here is just the Legendre. Hope that I spelled it correctly. Could someone give me input on it?
I think it's R-E.
E. The general rule for someone who knows no French is that basically you have to add additional letters that you don't pronounce it for some reason. So this is the Legendre equation, and just reading off the solution. Is actually is a Legendre polynomial, which is marked as P. So why do we call it a polynomial? Just because from this derivative, the only thing that we can get is a polynomial. No matter what is the value of L, it's still a polynomial. We have here our good friend -1 to the power of L, which was the reason that we put in as the normalization -1 to the power of L. Not that we add to it, just to connect it with the Legendre polynomial. And just let's write down a few. We knew it because we wrote y of 0, 0, and that we know is just a constant. Can't do anything with this, but a constant. So on and so forth. What we'll do now, our friend the mathematician wrote all kinds of properties of these polynomials. We'll just cite them and see what they help us. Orthogonality. Now, you can come from it from the point of view of mathematics and be surprised that you have orthogonal relations here. You can come from the point of view of physics and say, of course, they belong to an operator, they must be orthogonal. Now the -1 to 1 is just a cosine theta between 0 and theta.
And also the convergence ratio of Legendre polynomials.
Right.
Because if you don't have a singularity.
just a normalization. You can describe any spherical function as a combination of Legendre polynomials. Of course, again, because it's an eigenvalue and it's an eigenfunction, and an eigenfunction can be a basis of the space that we're trying to describe. A generating function. Remember the same type of function we had for the Hermite polynomial. Same if you just write it as a Taylor expansion of this function, you get the Legendre polynomials times s to the power of n. As we have seen for the Hermite polynomials, as you will see for Laguerre polynomials. And the recursion relation that usually pops up for these types of polynomials So once I have the first two polynomials, I can go and produce all of them. Okay. So what does it teach us? This is not much. It's just connecting a known solution from differential equations to our solution of the harmonic oscillator. We're still missing one thing. Actually, here we solved only the m equals 0 case. What happens if we are discussing a case where it's L and M is not necessarily 0? Remember in the beginning we have defined them as 0. Well, so you have another function of Lm rotation, not x. Okay, so this is the complete form of the Legendre polynomial. And as you see, that's what we get if we brute force solve the differential equation. It's the same thing that we got through the creation and annihilation operators, which was a different, to my taste, much easier route. Okay, I want to go into a physical property of these spherical harmonics, and that has to do with its parity. It's very important, let's say, for spectroscopy. Someone knows why?
What is the question?
Why parity is important for spectroscopy? Or in general, any property of a system that has conservation of angular momentum and it creates or annihilates a particle that it gives out. In spectroscopy, it's a photon. If the parity between those two states is either conserved or not conserved, the particle has to carry out this parity. So you can rule out all kinds of transition, let's say in spectroscopy, just by checking the parity of the solution. Okay, so if you remember, we did the parity operator, we discussed it at some months or a month and a half ago. So, to remind you, parity so what do we do when we operate on a wave function with a parity operator? We take R and turn it into minus R. Okay, so if I have x, y, z, I know easily what to do. Take any x, y, z and write down, instead of it, minus x, minus y, minus z. Well, but we are working here in spherical coordinates. So we have to take an R and change it into a different R, theta, and phi. Okay, but at the end of the day, if I have a vector pointing at R, theta, and phi, and I perform a parity operator, I send it to the opposite direction, right? So what happens to R?
Nothing. It stays the same because the it is
Right, so if I want to be precise mathematically, r is x squared plus y squared plus z squared square root of it. Doesn't change with minus a. But physically it's clear. I just reflected my vector. Nothing happens to r. The xy direction, just go to the opposite. I could write here also minus, it doesn't matter. And here, simply go to the other way around, which is pi minus theta. Okay. So, nothing can happen here from changing x, y, and z to minus x minus y minus z, which means that we can write a basis that is the same for pi and for L squared, meaning that any solution of L squared has to have a definite parity. It doesn't say if the parity is plus or minus, but it has to be either plus or minus. It can't have a mixed parity. So let's brute force it. We know to write down. So operating with the parity operator on YLN, brute force just wrote down the direct use of the parity operator. Okay. Okay, let's see what happens. Let's write it directly. So what happens to cosine of pi minus theta? Simply, very good, minus cosine. if we go back and check what are the Legendre polynomials of this guy, putting in instead of x minus cosine. So the combination of both guys so the parity of the function doesn't depend on m, it depends only on L. Okay, so what can we conclude from this whole game? Let's say, and this is an introduction to the hydrogen atom, and don't worry, I'm not going into it. Well, we have some Hamiltonian. In order for it to conserve angular momentum, what is the conditions that it has to fulfill?
It has to commute with L squared.
Has to commute with L square. Well, P square will commute with L square. Right? So any Hamiltonian will have the form of P square over 2m plus V of R. This commutes with L square. Does this commute with L square? I need an additional condition here. What is it? That it won't depend on R vector, but
it's a central potential, right?
A central potential, meaning that it depends on R, not on theta, not on phi. It has no direct dependence on R or theta, which is the meaning of this absolute value. If the Hamiltonian fulfills this, it commutes with L square, meaning the angular momentum is conserved. Okay, in this case, we have here, let's assume we have a three-dimensional potential, meaning it will depend on three quantum numbers. L and M we know, and there's an additional quantum number n, which is the additions that we will get out of solving the R-dependent part of this equation. Now we have another thing that we know. Let's write it this way. N goes between meaning that if we write down a table of L and M, so for 0 M has a value of 0, no more, one value. In general, 2L plus 1 values. Now, and that we'll see that N gets also integer values. 0 force, and you will see that L must be smaller or equal to. And an additional thing, again, I'm not proving, you'll see the proof. This is surprising. Now, it depends only on N for any potential, central potential. Meaning, if I combine all those conditions, so each energy value has a degeneracy the summation of 2L plus 1 till the value of N. You can convince yourself that the degeneracy is N squared. Therefore, for any central potential, the ground state has a degeneracy of 1. The second value N equal.
So N is strictly bigger than L, right?
L has look. It's better to look the other way around. Tell me the energy N. What are the values of?
Right. But
I think that it's better to put it in. Here they are usually. Okay, sorry about that. N's are. Well, it's a question of convention. It doesn't really matter. 1, 2, 3. Okay, not from 0, from 1, so L has to be smaller than N, but everything else that I said is okay. So the second energy state has 4 different values of L and M's, either L and M 0, 0, or 1 with plus minus 1 and 0, and so for the third you have 3 square, 9, and so on and so forth. And that doesn't depend on the explicit value of the energy, doesn't depend here on L and M. This degeneracy is everything that stands behind the periodic table, and now anyone who has looked at the periodic table first of all sees that the first 2 states, you have 2, not 1. How come?
You have 2 electrons.
You have spin, so an electron can be in 1 and 2, so you can fill out any NLN state by 2 electrons. The other thing that is a bit strange is that it starts to grow, that's fine. But at the third row it stops growing. And that is a result that electrons have interactions between them. This whole picture we forgot about interactions between electrons. We just put 1 electron in a state, and that's of course not true. The amazing thing is that still you can build this whole picture on the single electron states with some corrections. Otherwise our chemistry would have been much more complicated. Okay, as I said, I'm not going to go into the whole solution of the hydrogen atom in this course. We need for it at least 2, not at least, we need for it 2 lectures. We have only 1. So what I want to do in the last lecture is to discuss the clips that I have put online. So I ask you for the next lecture, just go over, see these clips. If you have questions, that's the place, because these things deal with the basics of applying quantum mechanics. So as I said, there's no complicated mathematics there. On the other hand, it clarifies the concept, and concepts are important for the exam. So I suggest take time, those of you who didn't see the clips, see it and come for the discussion in the next lecture, because I think it's more important than going through these mathematical properties to understand just what is a wave function, what is a Hilbert space, what do we do when we do a measurement, what does it mean to get all these questions for next lecture. And come with your own questions or clarifications or whatever you need. Okay, so let's start.
איפה ה-N מגיע?
ה-N מגיע מה-R, לא עשינו איתו כלום, נכון? כן, מגיע.